that is normal and abnormal, or normal and abnormal Zeeman effect. And second is the Stark effect. Stark effect is that again put that source of radiation in certain electric field, and that also causes changes in the spectrum. So there also spectral line gets displaced, and this effect is called as Stark effect. So both this Stark effect and this Zeeman effect could not be explained by this Bohr model or Bohr-Sommerfeld model too, and that's why people thought that there should be needed another advanced atomic model which will describe each and every property, physical and chemical property of almost all elements, as well as in case of molecules too, molecular physics. This particular theory should be able to give each and explanation of each and every observed effect, and in that sense these two concepts, as I said earlier, these concepts have been taken in consideration, and based upon that, these are the two names of the scientists, Goldschmidt and Uhlenbeck. We are going to write their names. These scientists came forward with this particular model, assuming that there are two main features are needed. So the first feature of this particular atomic model is the concept of space quantization. I don't know how many of you know this meaning of this word space quantization. Sorry, this is space quantization. We'll explain very finely what this particular space quantization is. And second important concept they have added is this electron spin. So remember, these two things are the basic foundation of this vector atom model, highest successful model. After this model, now we do not require any model to be modified or to be prepared or to be studied, and thereby we can explain the structure of the atoms and like that. So this particular first model, this particular first one of the very important model, that model gave us a clear-cut understanding of the atomic structure. So now how this looks, or what are these particular concepts, that we will see here one by one. So the first concept, let's go with the first one, that is the space quantization. Okay, now look this, these are very important concepts required entirely in this atomic and molecular physics. So space quantization, space quantization. Okay, look at here, in earlier case we have used this, okay, mvr is equal to n into h upon pi square. This is what our second postulate of Bohr theory. Okay, second postulate. Now this is one quantum condition. So here we have said that momentum is quantized. So we have used this condition, and we have said that momentum of an electron is quantized. Means what? I can have n is equal to 1, 2, 3, 4, etc. Only limited integer values are allowed, integral values are allowed. 1.2, 3.5, etc. These numbers are not allowed, or momentum of an electron can never have values like this 1.2 into h cross or 3.5 into h cross and so on. So this particular concept is called as quantization of momentum. Momentum is quantized, and this principle is called as quantum principle. So energy is quantized, momentum is quantized, and at the same time the space itself also is quantized. So this concept of space quantization is nothing but what? Here in quantum mechanics we have this quantization of momentum, quantization of energy, and the space quantization is again there. Okay, now what this concept, will write very short here as follows. The space quantization, means the electron orbits are quantized in free space. Yeah, quantized in space. Orbits of the electrons are quantized in space. Okay, and for that I'll just give a very simple example what this quantization means. Okay, now let's check. I am taking this one orbit here. Sorry, this would have been taken this way. Okay, this is one orbit. Now I am showing that this is what a center, and this electron is revolving like this. Okay, this is one orbit. If someone goes same orbit, if it is orientation changed and if it is made like this, so this orbit is also allowed or also possible. So this electron is moving this way. Okay, if someone goes for another orbit as shown by this. Okay, so in this case, this particular electron is moving as shown by this. If you want, you can draw this diagram. So here, this is the nucleus, and the electron around this nucleus, this is moving in orbit 1, orbit 2, or suppose some number as I have given, and this is what I am taking. So which orbit is to be a correct orbit, that is to be taken here. So in that sense, when I go for, this is a 3-dimensional picture, remember, this is 3D diagram, and in 3D diagram, so our atom is not 2-dimensional. When on paper we draw this atom, we draw this is nucleus and this is the orbit. This is 2 dimensions. When we add 3rd dimensions, then it looks like this. So when it looks like this, then this is the nucleus and this is atom. A particular electron in an atom can have this orbit, can have this orbit, can have this orbit, or in infinite number of orbits are possible. Okay, infinity number of orbits are possible. So out of that, which particular orbits are to be taken, and that particular concept is nothing but the space quantity. So selected orbits are allowed, and to measure that particular selected orbits, or to find out such type of selected orbits, we have to use here is a concept of, okay, that is what we have to apply certain, understand that we are applying certain external magnetic field in a particular direction as shown by this, some direction. And wherever this external magnetic field is applied, now these orbits orient, what I am saying, they are orient in some specified direction. Of course, this specification is provided by quantum mechanics. So the quantum mechanics tell you, whenever this particular atom is placed in an external magnetic field, now the orbits in which electrons are moving, these orbits cannot have any orientation. Any arbitrary orientation is not possible. Certain selected orientations are only possible, and this is the concept that is called as the actually it is called as the space quantization. Okay, so this is what a concept. Now we'll write in very short as it is possible. And when we go for, so in Sommerfeld model or Bohr model, we have 2D picture of atom. In actual case, the atom is of 3 dimensions. So when we go for 3rd dimension of 3 dimensions, now in this case, this question of orientation comes, orientation of the orbit, whether it is parallel to the plane, whether it is inside the plane, whether it is perpendicular to the plane, whether it is it is oblique to the plane. So different types of orbit, circular orbits are possible. Out of that, only circular, only selected orientations are possible. And this orientation of this particular concept is called as space quantization. Okay, so we'll write in very brief. And now there are 2 different types of quantum numbers we are using. So the quantum numbers which we have already defined in Bohr-Sommerfeld model, that is m, k, and n. Okay, n is the principal quantum number, k is analogous to orbital quantum number, and one more, that is m. So we have taken, there are 3 different types of quantum numbers in case of this Bohr-Sommerfeld model. Here also the same quantum number, but then the symbols have been changed. To how to change that symbol and how to understand this particular space quantization, that way we look as follows. Okay, so we'll write here the diagram shows okay, this is the diagram. The diagram shows many orientations of electron orbit. Okay, according to quantum mechanics, only certain orientations are allowed. Only certain orientations are allowed. Okay, and this is called as space quantization. Once again we are writing, this is called as space quantization. Okay, and remember, for that we have to use this concept L bar is equal to R cross P. This is called as angular momentum. Angular momentum. Just a minute. This is called as angular momentum. It's not writing. Oh, this closed. Okay, just a minute. Sometimes happens this way. So as I said, L bar is given by R bar cross P bar. That is angular momentum. Now for an orbit, any of the orbit, if I go for this orbit, now if I draw this orbit as shown here, okay, this is the orbit shown here, circular orbit. Now this is R and this is P, R cross P. Now use this right hand rule. So R cross P will show you this angular momentum has direction as shown by this L bar. If someone draws this particular orbit is like this, now in this case again this is your R and here this is P, therefore the vector which is representing L is now having this direction. So L bar, now here also in the earlier diagram too, I can draw different directions for L bar depending upon this orientation. So this L bar what I have drawn here, this L bar is the representation of the orientation. That means how this orbit is oriented. Suppose L is having this direction, means this orbit is like this. If L is having this direction, means again this orbit is like this, but the motion of the electron is opposite to earlier one. Okay? If in this case, if this is the motion of the electron direction, in this case this is the motion of the electron that is opposite to this, and that's why this L is downward direction, this L is upward direction. This L is here, L bar is here, means this orbit may be like this. So that is how we can go for different types of orientations and the directions of L depending upon orientation of the electron orbit. Okay. Now what we have to do here in this space quantization, we have to assume there is some external magnetic field H and this L bar, and we say that this L bar precesses around H. Like I think you might have seen this spinning top, ज्याला आपण मराठीत भोवरा म्हणतो. Okay, when this particular spinning top undergoes a motion, it precesses around under the gravity, and what that precision, I think you might have observed the motion of that spinning top around whenever it is in motion, and that type of motion is called as precession motion. So here also this orbital angular momentum vector or angular momentum vector precesses around this L bar, and this precision is a very selected type of precisions are allowed. According to quantum mechanics, this precesses in such a manner. Hello?
सर ते स्क्रीन दिसत नाहीये सर.
ओके. अरे मिकल काय चाललंय? मिकल काय सांगतोय तुला? इतकं काय सांगितलं? I have drawn lot many diagrams. बरं एवढे डायग्राम. काढा ह्या सगळ्या डायग्राम. लगेच सांगायला पाहिजे ना. So this what I said. This L bar is given by R cross P, that is angular momentum. Now if I take this, आता मी diagram काढतो. This is first, this is second, this is third, this is fourth, and this is 5. This is why spinning top. Spinning top. This top precesses around, okay, under gravity. I don't know how many of you know this particular classical motion of the precessing top. So that is called as the phenomenon that is called as precession. So here this L bar also precesses around the direction of this H bar. So remember in the diagram 1 I have shown this to be the path, the motion of the electron, and therefore R cross P in this case gives me direction downward of this L bar. Here it is in the clockwise anti-clockwise direction. So this L bar is in the upper direction or the up direction. Here this is the direction of this motion, second diagram. The orbit is oriented like this. So L bar is shown to the left hand side. If I change the direction of motion, the L bar may becomes towards the right hand side. Diagram 3. This is what a circular diagram. This is what a circular orbit shown here of the electron. And when I go for this L bar is equal to R bar cross P bar, this right hand side gives me direction of this L bar is this. Then if any other arbitrarily another or some angle is taken, some other angle is taken, in that case again R cross P gives you some other different direction of L bar. Now as I change the orientation of this orbit, this direction of L bar goes on changing. As long as there is no any magnetic field is applied, you are allowed to take any direction from this L bar. But when certain magnetic field is applied to this particular source or that particular material or that atoms, then this L bar and H bar align in such a manner that it has to satisfy certain condition, or that is called as quantum condition. And wherever we understand these quantum conditions, that is nothing but the quantization of the space. Okay, again we'll write it brief over here. So right here okay, we'll write here diagrams show different orientations. In our textbook it is something different orientations of L bar. Diagram show different orientations of L bar. If H bar is external magnetic field applied, H bar is the magnetic field applied. Okay, so I am showing this here diagram. I am showing this diagram here. This is my H bar, and suppose the motion of the orbit is such that this L bar is shown by this. This is L bar. So naturally this electron is revolving around this orbit as shown here. So this is the orbit, and therefore this is L bar from the center, and this is the angle here. I am calling it to be alpha. So this is the direction of H bar, this is the direction of L bar, and angle shown is to be alpha there. Okay, we'll write it there. The angle between directions of L bar and H bar is alpha. Okay, the vector L bar is perpendicular to the orbit of an electron. It is perpendicular because of the condition L bar is equal to R bar cross P bar. That's why it is perpendicular. This due to quantum conditions. Okay, remember these quantum conditions are by nature, not by me or you or anyone else who wanted to put these conditions. Okay, it is by nature. The quantum conditions, the angle takes certain discrete discrete values only. Due to quantum conditions, the angle takes certain discrete values only, and this gives rise to the certain orientations of orbits. This gives rise to a certain orientation of orbits with respect to direction of H bar. This gives you orientation. This gives rise to the certain orientation of orbits with respect to the direction of H bar. Okay. Thus electron orbits are quantized. This is actual concept. Electron orbits are quantized in space. Electron orbits are quantized in space. Okay, and this is called as space quantization. This is called as space quantization. This is called as space quantization. Now let's take use of this. How this space quantization plays a vital role here. We can see here now, and the quantum number because of this space quantization is called as magnetic quantum number. Okay, the quantum number due to space quantization is called magnetic quantum number. Magnetic quantum number. Okay, I think you might have used this earlier in SYBC or studied earlier in SYBC, but try to understand. So what are the how the third quantum number comes there? So first quantum number is Ln, principal quantum number. L is orbital quantum number. Because of orbital motion, L takes different values. And third quantum number we draw, this is called as Ml, and that is coming because of this quantum conditions of the space quantization of this L. L cannot take any values, L takes only selected values, and accordingly whenever it is kept in certain magnetic field, and accordingly this Ml is the projection of L on the direction of H, and these are the values of Ml. So these are the three new quantum numbers this vector atom model uses. Whatever quantum numbers earlier we have used in Sommerfeld model, Ward model, etc., they are okay there, but they are not directly used in this quantum, this vector atom model. Okay, so let's write it here in brief. The quantum numbers used in vector atom model. Quantum numbers used in vector atom model are small n, L, and Ml. Okay, rather than N, K, R, etc., we are using N, L, and small ml as per quantum mechanics. As per quantum mechanical conditions or as per quantum mechanics. Okay, these are okay. So N is principal quantum number. Principal quantum number. Okay, the same which we use in Bohr orbits. So this principal quantum number, and we know that this N varies from the minimum value is 1, 2, 3, and so on infinity. So there is no restriction upon value of N. N can take any values from 1 to infinity. This is first quantum number we are using here. More about this we are going to discuss later on separately. So second is L. Now in Sommerfeld model we have seen this ellipticity of the orbits. Okay, so when the circular orbit is this, we call this L to be 0. When L is equal to 1, this circular orbit has maybe this type of elliptical orbit. So this is what a number which is associated with this orbital angular momentum of the electron. That's why the second quantum number L is called as orbital quantum number. Orbital quantum numbers or number, and the value of this L goes from 0, 1, 2, 3, etc. up to n minus 1. So first fix n, and based upon that L can take again n values starting from 0 to n minus 1. So wherever it is 0, it is spherical orbit. Wherever it is 1, now ellipticity of this orbit goes on changing, and maximum value of L is n minus 1. Okay, we are going to see some examples there again. And third quantum number Ml, n suffix L. This is called as the orbital magnetic quantum number. Okay, try to understand the difference between these two. Orbital magnetic quantum number. Okay, why we are writing this way? Now because one more quantum number we are going to introduce later on, that is called as spin magnetic quantum number, that is ms or s. Sometimes we use s, sometimes ms. And here this orbital quantum number and orbital magnetic, here we are not applying any magnetic field, but here whenever magnetic field is applied, this L, capital L, takes certain selected values or orientations of this angle, takes certain values. Accordingly, projection of this L bar on ML, on H, that gives me values of ML, and these values are given by this simple formulation. ML takes values from minus L, then minus L plus 1, goes on increasing, becomes 0, then 1, 2, 3, etc. up to plus L. Okay, up to plus L. So minus L to plus L including 0 as a permanent. So these three things we have to understand. This is called as the quantum numbers that are used in this vector atom model. Okay, so write it explicitly. So these are the three quantum numbers we are using. One more thing. Again, remember, all this entire vector atom model theory came after quantum mechanics. So once this quantum mechanics was developed, then people use this particular quantum mechanics to understand this model, vector atom model. Therefore, most concepts in this vector atom models are taken from the quantum mechanics. So whatever we have discussed earlier in Thomson model, in Bohr model, in Rutherford model, in Summerfield model, most of the classical concepts were used there. Now we are using some quantum conditions or quantum concepts, and therefore here we have to go for calculation. Once this small l is defined, how to calculate capital L. Once this small ml is given, how to calculate capital L. Or this s is small ms is given, spin quantum number is given, how to calculate total spin of the system, etc. This calculation go from according to this quantum mechanics. So write further statement. According to quantum mechanics, the orbital angular momentum, okay, this is actual physical quantity. This L is quantum number, it is purely number, while this orbital angular momentum, it's an angular quantity of an electron is given by L is calculated. Either I can use R, in classical mechanics I can use R bar cross P bar, but here in quantum mechanics, if this small L is known, L bar is given by L into L plus 1 into H upon twice Y. Remember, I am sure very few students will understand why this type of relationship is written. For that, first you have to learn quantum mechanics. Actually, quantum mechanics is in our second term, but here we have to assume that once this angular orbital quantum number is known for an electron, so its orbital angular momentum is given by this relationship. Okay, why? This Y has no answer at this point, because for that we have to learn quantum mechanics first, and then we have to use this particular concepts here. Then you will understand this. But it doesn't matter. This is not required at this here. So once this orbital angular quantum number is known, from that orbital angular momentum is given by this particular number. Okay. Next, the projection of L bar. The projection of L bar on the direction of H bar. Now we know how to go for projection of one vector with the other vector, etc. So we can use this on field on H bar. Okay, and usually direction, for convenience, direction of H bar is taken as along Z axis. For convenience, there is no hard and fast rule, for understanding only. H bar is taken along Z axis, has magnitude. So when this L bar is projected along the direction of H, which is usually in the Z direction, then this component of Z in the direction, L in the direction of Z is given by now this number ml into H upon twice Y. So these two equations, okay, this equation and this equations, they are directly taken from quantum mechanics. As I said earlier, you won't understand why they are included here, but they are to be included because your vector atom model is completely based upon quantum mechanics principles. So for that, we have to understand this. Lz is given by ml into H upon twice Y, where this ml is orbital magnetic quantum number. Orbital magnetic quantum number. Okay, we'll go for some special examples, then we'll understand it very easily. Okay, now how this is done? This diagrams, actually I could have borrowed it directly from internet, but before that I'll just go for a very simple diagram here. Okay, now suppose this is my z-axis. I just include this. Let me take the line from this. Line is here, so I'm taking this line to be z-axis. Okay, this is my z-axis. Okay, that's good. And take this to be origin. This is the origin. And now take this to be value of L. So this is what example I am putting. L is equal to 2. L is equal to 1. We will show it later on. L is equal to 2 is this. Now draw a circle, half circle from this L in such a manner to become this. So this is what I am drawing a vector diagram. And now this is my value of L. Okay, now take the same L, can have this orientation. I draw this. So this is again L. If its projection is taken, now projection of this will be taken here. This now, and then this is given by ML is equal to 1. I can have orientation of this L is such that it goes this direction. So this is another orientation. So this is again L. So if its projection is taken here, I'll get this value of ML is equal to 2. Similarly, here also I can have this orientation possible. Okay, and therefore its projection on this H or Z direction is given by ML is equal to -1. And lastly, this is what a quantum condition tells you. This is the fifth orientation possible. Again, this L, its projection over this goes from ML equal to -2. So ML, when L is fixed, L is equal to 2, ML varies from -2 to +2. Okay, ML varies from, ML goes from -L to +L including 0. This is what I have taken. So L is equal to 2, so ML is equal to -2, to ML is equal to +2. In between is -1, 0, 1 and 2. In between value is never possible. Accordingly, this L cannot take this particular value, and because this projection of this will be 1.5 times, okay, 1.5 times h upon twice pi. Quantum mechanics doesn't allow this. Therefore, ML must have either 0, 1, 2 or -1 or -2, and that orientation is only allowed along this Z direction or this H direction or Z direction. So this is called as space quantization of L bar or small l over this direction of H, and that's what I got 5 different values of ML, which is ranging from -2 to +2 as shown by this calculation. Now same diagram we can draw for another, that is I can draw it for, okay, now this is what, now look at here, according to quantum mechanics, to calculate this L bar I have to go for this calculation, L into L plus 1 into H upon twice pi. So using this I'll get L bar in this case is 2 into 2 plus 1 into H upon twice pi, or that gives me L bar in this case is 2 into 3 is 6 in the root 2. So it is root 6 into H upon twice pi. This is the value of orbital angular momentum, physical quantity, when I have this orbital angular momentum value small l is equal to 2. Now you can repeat this example for L is equal to 3. Now quantum mechanics or quantum conditions tells me that ML varies from -3 to +3 only, and accordingly now I am drawing this vector. Okay, if this value is equal to 2, this L in this case may be bigger than that. So this is L is equal to 3. It is its first projection. Again, This is what I am drawing this again here. This is my z-axis or the direction of h bar. So draw a circle, half circle of the radius equal to 3 units, and get the projections of this. Now one of this is this direction possible, so this projection gives me, now we have to draw such hundreds of diagrams later on. So ml is equal to 1. This orientation for L is equal to 2 is possible. This is equal to the second orientation, so its projection is given to be ml is equal to plus 2, and third mode is also possible as shown here. So this orientation gives me ml is equal to plus 3, and similarly downward also we can show 3 such possible orientations, and that gives you, this is ml equal to minus 3, this is ml equal to minus 2, and this is ml equal to minus 1. So ml equal to minus 1, ml equal to minus 2, ml equal to minus 3, and that is how here I can draw this L bar by this formula again, L into L plus 1 into h upon twice pi. So when I use it there, this is 3 into 3 plus 1 into h upon twice pi. 3 into 3 plus 1 is now root 12. Root 12 is bigger than root 6, try to understand. So h upon twice pi. So here L is equal to root 12 into h upon twice pi, and here this L is equal to root 6 upon h pi. Now what is quantum mechanically measured angular momentum and what is classical mechanically measured angular momentum? That has some notification, after some change, some difference, notation difference is there, and that is how these two diagrams, that is the diagram that gives us the value of the, that is the concept of the space quantization. So this entire concept, I think you have understood this concept of space quantization. So where we have started, space quantization is that orbits, any arbitrary electron orbits are not possible when the source of radiation is kept in certain magnetic field. Quantum mechanics compares these orbits to take only certain orientations, and this concept is called as space quantization. This concept is the foundation stone of this vector atom model. Try to understand, this is very essential and important concept we must understand. Once we understand this concept, then and then we will be able to, जे आता पुढे जाऊन जे काय आपण इलेक्ट्रॉनिक कन्फिगरेशन लिहितो 1s2 2s2 2p6 etc., that is possible only because of this type of space quantization. So this is the first point we have discussed in today's discussion, and the second basic aspect of this is said to be the electron spin. Electron spin. Out of this, here the diagrams which I have drawn here, these diagrams will be needed to be drawn several times in chapter 2, chapter 3, chapter 4, again and again. So at that time we should understand this particular, how the way or interpretation of these diagrams as shown by this. Now till now we have only 3 quantum numbers, that is, I will write it that form, but these are the m, l and ml. So according to scientists at that time, these 3 quantum numbers are sufficient to locate a location of electron inside an atom. म्हणजे कुठल्याही ॲटम मधलं इलेक्ट्रॉनचं लोकेशन झालेलं असेल तर तुम्हाला हे 3 क्वांटम नंबर सफिशियंट आहेत असं वाटत होतं. वाटत असं वेगळं. नाउ दिस क्वांटम नंबर मीन्स जस्ट लाईक आपण जसा ॲड्रेस लिहितो, what is that in address we required? First we require name, then we required your address. Address consists of तुमचं घर असेल, लोकेशन, नाव असेल, काय रोड वगैरे असेल, रोड, नेम ऑफ द हाऊस किंवा गल्ली किंवा जे काय असेल. देन वी रिक्वायर्ड दी प्लेस, म्हणजे तुमचं कोणतं गाव आहे. इफ प्लेस इज गिवन, आय रिक्वायर्ड तालुका, इन विच तालुका दिस पर्टिक्युलर लोकेशन इज दॅट, and then I required the district too. So with this, म्हणजे मला लक्षात घे की माझं माणसाचं नाव सारखं आहे किंवा जे एका जिल्ह्यातील 2 माणसं आहेत त्यांचा तालुका सारखा आहे, एकाच गावातले आहेत, ठीक आहे, एकाच गल्लीत राहतात, पण त्यांची नावं वेगवेगळी आहेत. सो दीज आर 2 डिफरंट ॲड्रेसेस. सो दिस इज कॉल्ड एज ॲड्रेस सिस्टीम, दॅट इज यूज्ड इन पोस्टल सिस्टीम. पोस्टामध्ये आपण ही ॲड्रेस लिहितो आपण, कुणाचे लोकेशन सांगायचं तसं. तसंच ॲटममध्ये टू लोकेट ए पोझिशन ऑफ एन इलेक्ट्रॉन these 3 quantum numbers were supposed to be sufficient, but later on it was found that basically a sodium spectrum. What is that? That sodium spectrum, I might think you might have studied. That is called as a sodium doublet. Now sodium doublet, and these sodium doublets are the two spectral lines which are having, this is lambda 1 which has a wavelength of 5890 angstroms, and second lambda 2 closed doublet, its wavelength is 5896 angstrom. So this difference is simply 6 angstroms only. Now this small deviation between the difference between these two spectral lines of, this is called as sodium D lines. Okay, this is sodium D lines. In spectroscopy, these are the sodium D lines. These are very close to each other. 5890, 5896. So these are the two wavelengths which are separated just by 6 angstrom. This type of phenomenon could not be explained by this vector atom model too, because there is again missing something, and what is that missing? This is what nothing but the electron spin. So to solve this difficulty of this sodium doublet, or this again fine structure of the spectral line, Goldschmidt, I read the names of the scientists. S. Goldschmidt, Goudschmidt, okay, Goldschmidt, and G. Uhlenbeck, Uhlenbeck, Uhlenbeck proposed the new concept of electron spin. Now from where this concept came? Can anyone has idea? Kunaला सांगते का हा concept कशाने येऊ शकतो? Now take an example of this is Earth, and we call this to be a moon. Okay, so moon revolves around Earth, at the same time it spins about its own axis. So this is orbital motion as well as spinning motion. Same is the case of Earth. Earth itself is moving around the sun, as well as it is moving around its revolving around its axis of rotation, and that's why we are having days and nights and all that. So this type of physical situation, or this type of physical example, it has two different types of motion, that is orbital motion, and second is nothing but the spin motion. So actual classical spin. So in orbital motion, Earth revolves around sun, and in spin motion it revolves around its own axis of rotation. So these two types of motions must be for an electron. If it is moving, if it is revolving, it is revolving around the nucleus. If it is revolving around nucleus, it also must have certain orbital motion as well as an spin motion. Okay, so this is what a picture I will draw here. This is the nucleus Ze plus, and this is an electron. So it is spinning about its own axis, and at the same time it has having this orbital motion. This is velocity v, and therefore we have L bar, that is the angular momentum because of this v, and at same time because of this S we have some S bar, or that is called as spin orbital angular momentum. Orbital angular momentum. म्हणजे लक्षात घ्या, दोन प्रकारच्या मोशन्स त्याला असतील, त्याच्यामध्ये दोन वेगवेगळ्या प्रकारचे अँग्युलर मोमेंटम आणि दोन वेगवेगळ्या प्रकारचे मॅग्नेटिक फील्ड्स, स्पिन मॅग्नेटिक मोमेंट as well as angular magnetic moment. So spin orbital angular momentum is thought by these people. So this is one of the basic necessity of this vector atom model. But note here in this case, in actual quantum mechanics, this actual physical revolutionary motion, that is self-revolutionary motion of electron is not there, but the electron is assigned some intrinsic spin. Okay, in intrinsic, intrinsic spin means there is some spin is assigned by nature to the electron. Electron is not needed to revolve about its axis because electron itself is so small. Electron is so small. If it starts revolving about its own axis, its velocity will be more than velocity of light, and this is not possible according to STR. So special theory of relativity restricts velocity of anything more than velocity of light. So if electron, as per this particular planetary model, if we go for actual motion, if we try to find out electron is moving, revolving about its own axis, its energies and its size is so small that its orbital velocity, its spin velocity will be more than velocity of light. This is not possible, but still it has some magnetic property because of what, that is called as the intrinsic spin. म्हणजे लक्षात घ्या, जसं इलेक्ट्रॉन हा रिव्हॉल्युशनरी मोशन मुळे त्याला एक मॅग्नेटिझम तयार होतो N आणि S, तसंच त्या स्पिन मोशन मुळे सुद्धा त्याचा एक छोटासा मॅग्नेट तयार होतो. That also gives to be a magnet like N and S, and that is what this is called as intrinsic spin. This spin is provided by nature to the electron, which gives rise to certain magnetic movement. I am sure these things are not that easy for you to understand at this stage. कदाचित तुम्हाला याच्यापूर्वी तुम्ही अभ्यास केला नसेल त्यामुळे समजणार नाही, पण जसं इलेक्ट्रॉनचा किंवा कुठल्याही ॲटम मध्ये मॅग्नेटिझम जो येतो तो मॅग्नेटिझम ह्या इलेक्ट्रॉन मुळे येतो. Electron is a positive charge, it undergoes this type of accelerated motion and this gives rise to a magnetic moment or the atom becomes a magnet because of the electron. Electron itself is a magnet because of the motion or the charge it has. So there are two different types of magnetism associated with the electron. One is because of this orbital motion and second is because of the spin motion. Even though electron doesn't spin, it has spin magnetic moment, and in that sense म्हणजे त्याला स्पिन मॅग्नेटिक मुवमेंट आहे याचाच अर्थ त्याला काहीतरी इंट्रिन्सिक स्पिन प्रोव्हाइड केलेला आहे बाय नेचर. सो दिस कन्सेप्ट वॉज वेल डिस्कस्ड बाय द Goldsmith and Uhlenbeck. They have taken this concept in consideration, and based upon that, this spin also, if it is kept in certain magnetic field, it will have again a quantization. So there are two possible values, either spin S half or minus half, and this fourth quantum number is now sufficient to locate location of any electron inside an atom. And once this is known, then we can give a successful explanation of the 2D in a sodium doublet. Sodium doublet is the explanation. That explanation requires this concept of the spin, intrinsic spin, and the spin quantum number is additional quantum number there. So along with this M, L, ML, one more quantum number, that is MS or spin quantum number is required, and that is the requirement of the situation, requirement of the by nature itself, and therefore our vector atom model possesses 4 different quantum numbers. So about this we'll write in brief and then we'll stop. Next lecture we'll go for actual description of all these quantum numbers and so many things. Okay, so let's write here brief. Adit will get up here. Right here. According to, this is again due to quantum conditions, quantum mechanics. According to quantum mechanics, the spin of electron, more about this if you want to read very in detail and understanding this entire concept, go for Baiser, B-A-I-S-E-R. Okay, Modern Physics by Baiser. You will get a very nice concept described by this, or Feynman series, Feynman books. They also have this, or go to the Wikipedia and just give a title electron spin. Entire very nice lucid information has been given on Wikipedia. You will understand this. So according to quantum mechanics or quantum theory, the spin of electron should be quantized. should be quantized. So nature is such that everything is to be quantized. Everything, energy, momentum, whatever that is to be quantized. So the spin also of electron is also to be quantized. Hence a new quantum number. Hence a new quantum number. Hence a new quantum number called as spin quantum number. Called as spin quantum number is introduced. And remember, for this simple discovery or nice discovery, these two people got Nobel Prize at that time. Okay, so introducing this concept, discussing its logic, discussing its necessity, and solving problem, this particular thing led to a Nobel Prize for this. Actually, these were students at that time. So those who put this condition around 1920 or 23 somewhere. So those were students, and they put these conditions, and then electronic configuration now is whatever electronic configuration we are able to write is because of these fellows who introduced this particular concept of this electron spin. Okay, so that is what we introduced this. And okay, so that's how this is this quantization of spin. Okay, and hence the atom model based upon, hence the atom model based upon these quantized vectors, QUANTISED, TIZED, these quantized vectors is called vector atom model. This is called as a vector atom model. More about this, see our textbook, see the references as I said earlier, or go to the Wikipedia. You will get more and more information about this. So here also this so if this angular quantum number is known according to quantum mechanics, capital S, the total spin quantum number is given, spin angular momentum is given by root of small s into s plus 1 into h upon twice pi. Just like we have one for this L, orbital angular momentum quantum number is known. From that orbital angular momentum, capital L is calculated by root L into L plus 1 into h upon twice pi. Similarly here also, if spin is quantized, then the spin angular momentum of an electron is given by root of small s into s plus 1 into h upon twice pi, where this small s is said to be small s is said to be spin angular momentum quantum number. And remember, S is a quantum number, its value capital S is equal to 1/2. Capital S is equal to 1/2. Sorry, this is spin, actually spin quantum number, not capital S. Spin quantum number is 1/2. Now one very interesting example of that has been given. So that electron has half spin. What do you mean by half spin? Okay, now suppose we have a human. Okay, this is a person. If he revolves in 360 degrees, that is one complete rotation. Okay, let's take one common example. Person required a one complete rotation to look what he was before. म्हणजे एखादा माणूस तुमच्या समोर उभा आहे, तो जर अर्धा म्हणजे तुमच्या अपोजिट त्याने बघायला सुरुवात केली तर तो मागून तुम्हाला ओळखायला माणूस तो ओळखायला येणार नाही, ओळखीचा असला तरी. म्हणजे त्याला पूर्ण एक रोटेशन घ्यायला लागेल तुमच्या बाजूने, तुमच्या समोरून. देन यू विल आयडेंटिफाय दिस पर्सन टू बी द सेम पर्सन व्हॉट वी आर लुक्ड अर्लियर. म्हणजे त्याचं रोटेशन होण्यापूर्वी जो पर्सन होता तो मला तसा दिसायला लागेल. हाफ स्पिन पार्टिकल्स आर सच दॅट they are needed to rotate only 180 degrees. Half rotation नंतर you cannot identify the electron which I had seen earlier, and electron now I am seeing इज द सेम. याचा अर्थ असा माणूस घ्या की त्या माणसाच्या दोन्ही बाजूला जसं पुढे डोळे कान नाक आहे तसंच मागच्या बाजूला पण त्याच प्रकारचं डोळे नाक कान आहे आणि तो असा गोल फिरल्यानंतर ठीक आहे. कुठलाही माणूस आपल्या नजरेसमोर आला की त्याच्या चेहऱ्याला जसा पुढे चेहरा आहे तसाच मागच्या बाजूने पण चेहरा आहे. मग त्याला 180 डिग्रीज मध्ये फिरवला की तुम्ही आता ओळखू शकत नाही की मगाचा तोच होता की आता तोच आहे. ओके, so this is the concept of actual spin here. So in case of electrons has such a nature that even if it completes half a rotation, we cannot identify whether the electron was that electron or now electron was the same. म्हणजे आताचा की पहिला हा वेगळा वेगळा आहे का नाही आपल्याला सांगता येत नाही. So in that sense, this electron is supposed to have this type of spin. Again, remember, this is by nature. Nature has made or given this attribute to the electron that it has spin is equal to half, whereas we human, we have spin is equal to 1. हाफ स्पिन आपल्याला कधीही माणूस ओळखता येत नाही. हाफ स्पिन जर असायचा असेल तर आपल्याला दोन्ही बाजूने चेहरा असला पाहिजे, पुढच्या आणि मागच्या बाजूने. असं होऊ शकत नाही. फिजिकली इट इज नॉट पॉसिबल. सो क्लासिकली वी हॅव आवर स्पीड p equal to 1, whereas this electron has its spin to be half, okay, 1/2. Okay, and therefore when I go for this quantization of this, okay, I can draw the diagram here. So this diagram shows you okay, again I will draw this particular line here. This is my h or z axis, and in s, this is the value of s. Okay, value of s is never equal to 0. Okay, so this is never possible. इथं हा spin असणार नाही. Either it will have this spin or therefore there only two orientations are possible. This is plus 1/2. ms is equal to plus 1/2, and this orientation gives you ms is equal to -1/2. So this is space quantization of spin. Space quantization of spin is given by this. So this is small s, this is also small s, and it has only two values possible, that is +1/2 and -1/2, and this is what is space quantization of the spin. Okay, so here this particular discussion of this vector atom model is complete. So what we have got now, for an electron, this vector atom model, we have 4 quantum numbers: L, we have L, we have ml, and we have 4th quantum number, that is s. And that's what I think you might have seen this earlier. If n is equal to 1, I will have L is equal to 0 and 1. If L is equal to 0, ml will have value equal to 0. That means plus L to minus L is only one value, that is 0. And other value of ml in this case is -1, 0 and +1. So these are the 4 possible values of ml when we have L is equal to 0 and 1. Then n is equal to 2, I will have L equal to 0. Sorry, this is, we have wrong here, we have the n is equal to 1, L can have only one value, that is L is equal to 0, and ml can have only one value, and at the same time we require this spin to be either +1/2 or -1/2. Okay, then n अनमग त्याचे इलेक्ट्रॉनिक कन्फ्युजन आपण लिहितो क्वांटम नंबर्स n equal to 1, 0, 0, and then this is equal to +1/2. So electron in this case 1, 0, 0 and -1/2. These are the two different postal address of an electron inside an orbit, inside an atom. So that is how here also, actually we are going to discuss more about this in the next lecture. So here L will have two values, so and ml will have values, L will have values 0 and 1, and now ml will have values, one is 0 and second value ml, okay, is this, and next value of ml will be for L equal to 1, it is -1, 0 and 1. So accordingly ml will have 4 different values, and for each again +1/2 and -1/2 spin may be there, and therefore we get 2 + 2 + 2 + 2, that is 8 number of electrons are possible there. here there are two number of electrons are possible, and that's why the principle we use twice m square, that is the total number of electrons possible in an orbit is given by 2 into 1 for the first orbit, raised to 2, that is 2. In the second orbit I get 2 into 2 square, that is 2 into square is 4 into 2 is now 8 electrons are possible. For n is equal to 3, we will have 2 into this n 3 raised to, that is 2, that is 3 into raised to 2 is 9 into 2, that is 18 number of electrons are possible. So whatever this electronic configuration we write, like 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Now for this third orbit we have 2 plus 6 plus 10 is 18, 2 plus 6 is 8, and 2 1s2 2, that is 2. That is because of, so this particular concept of electron spin is quite important in this case of vector atom model, and because of that we are able to write this electronic configuration. So this concept developed by Goldsmith and Uhlenbeck, that is one of the very fundamental and important concept of this quantum mechanics, and in vector atom model this concept has been taken in consideration, and accordingly now we have 4 quantum numbers rather than 3 quantum numbers. So both observatory model etc. has only 3 quantum numbers, but that quantum numbers of that particular models were not able to explain each and every detail of this spectrum, basically this fine structure or the sodium D lines, doublet sodium. These could not be explained by this particular model, that is called as this Bohr model or Sommerfeld model, and therefore the fourth model, important model that has been discussed by these picture people, and that is called as the vector atom model. Okay, so here we will stop today. Tomorrow or the next lecture, tomorrow we are going to meet again. We are going to see the next, that is again important things, one by one, each and every quantum number, its description, its values, its interpretation, precision, etc. All these things will be discussed in tomorrow's lecture. So 1.5 hours I will be taking tomorrow again, and on Saturday also or Sunday we will go for remaining small article, that is Frank Hertz's experiment and its interpretation, etc. And we will go for certain numerical problems also with this chapter. So up to Saturday we will finish this chapter number 1, and that will be helpful for us for this coming examination. Okay, so I'll just stop it here. Let me take the attendance, and